Okay, so we're going over the problems that we left out in the lecture because of the in interest of time. So we're going to start out with composition of functions. Problem 12 from the review sheet. So composition of functions. All right. Composition of functions. All right, so 12a. Looking at 12a. So for 12a, we have, they ask us to find f composed with g if f of x, by the way, f of x and x are interchangeable. F of x means that the function f depends on x, and f is just basically the function symbol itself. So f of x is equal to x squared plus 2x, and g of x is equal to 2x plus 1. And they're asking us to find f composed with g of f. And as I said before in class, the order does matter. So f composed with g is the same as f composed with g, meaning f with g being the input this time. What is g? G is the rule, the function rule, 2x plus 1. That's what g is. So wherever I see g or g of x, I'm going to put 2x plus 1. All right, so what does f do? What does f do? What does f do? Before I look at what f does, I need to first rewrite my g. So I'm rewriting g as 2x plus 1. And what is happening to g is that f is doing something to g. What f is doing is that f is squaring its input, right? And then it's adding 2x. So now what's happening is g is also being doubled. So not only is g being squared, it's also being doubled, all right? I'm going to ask you to just watch the video. It's easier for you to watch the video and rewind it than for me to be saying the same thing again. So I know it's a lot, it's a mouthful. Please watch this again. All right, now you can actually expand this. It's not very important. You can actually leave it the way it is. So that was your solution for 12a, f composed with g. All right, so let's move on to 12b. All right, 12b, again, kind of a similar problem. 12b, again, we are composing functions. So 12b is a composition problem. And so we are given that f of x is equal to the square root of x. And we're given that g of x is equal to x minus 8. All right, so g of x is x minus 8. And so now we're asked to find the composition in this specific order, f composed with g, which we know is just going to be f taken in g as an input. Well, what is g? What is g? G is going to be x minus 8, right? That's what is given to us. What does f do to its input? What does f do to its input? Well, f does this to its input. It takes the square root of it. So now I'm going to be taking the square root of that. And that's going to be my answer. Just taking the square root of x minus 8. All right, so let's move on to 12C. All right, so 12C. Okay, then. All right, good. It's 12C. This time we're going to reverse the order. We're going to try to work with G composed with F. Okay. So, here we go. 12C. We're trying to find G composed with F. So f of x is equal to negative x. In other words, what does f do to its input? It changes its sign. It takes the negative, opposite of it. And g of x is equal to x cubed plus 5x squared. All right, so now we're trying to find not what f does to its input, but what g does to its input. That's what we're thinking about, because we're trying to find G composed with F. Well, G composed with F is just basically you now making F the input. So F is the input. All right. So therefore, it makes sense to think about what F is, right? So F is negative X. So negative X is your input this time. But input into what? Well, input into G. What is G doing? G is cubing its input and then squaring it and multiplying the square by 5 and adding it back to the cube. All right, so now I'm gonna have negative x, which is now my new input into G. So wherever I see x, I'm gonna be putting negative x. All right, wherever I see x, I'm gonna be putting negative x. So then I have negative x cubed plus 5 times negative x squared. Of course, you can simplify this if you want. Show the mathematics, you know. So this is just going to be equal to, if you take the cube of something negative, you still maintain a negative, an odd number of negatives in a product. Still yields a negative, right? So I have negative x cubed. Now, if I square something positive, it's basically does not change what was there before I took a negative of it. So negative x squared is the same as x squared, basically. That's it. That's your answer. All right, that's your answer. Oh, all right. Sorry for the other paper below. I ask you to ignore that. All right. Okay, so let's look on another one, something with a fraction. So 12D, we have these two rational functions. So we have these two rational functions. Should I do that? Okay. Okay, no rational functions. I was skipping ahead. So 12D is f of x is equal to x squared, and g of x is equal to 3x squared minus 4. And now we're being asked to find g composed with f again, which we said before is you taking f of x as an input. You're taking f of x as an input, and then you're operating on it with g. What does g do to its input? What does g do to its input? It squares it first, and then it multiplies it by 3, and then it subtracts 4. So that's what we're going to be doing. So let's look at the input. Input is f of x, so that's going to be x squared is the input. And what's been done to the input? I know this is a little funny this time because you're squaring a square, right? So remember this, g squares is input. So g is going to square something that's already squared. And now you're subtracting 4 from that. So what you end up with is 3x to the 4th power minus 4. All right, so that's number 12. That was it for composition. Now we're going to be applying the principle of composition to something called inverses. All right, so we're going to be thinking about inverse of functions. All right. All right, so the inverse of a function is basically, simplest way to think of an inverse of a function is something that is composed with the function, original function, to give you what we call the identity function. So before we go to inverse, let's define what the identity function is. All right, so the identity function is a function f of x is equal to x. All right, or for lack of confusion, I don't want to use f of x now. Just say y equals x. That's the identity function. Basically, what's identity? Something doesn't change with operation. So I'll take the x value, put it inside the function, I get back the x value. All right, so it's basically what we have here is the linear function y equals x. Doesn't matter what you put in inside, you get back the same thing. If I put a 2 in, I get back a 2. The process of having an identity is the process that leaves something unchanged. That's what the identity function is. It leaves the input values unchanged. All right, so again, that's what composition of a function with its inverse does. It brings you back to the identity function. All right, so here is an example that I did in class. Let's do it again. So number 13, A. So I start with f of x is equal to 2x. All right. And I want to prove that these two pairs are inverses of each other, right? So I have f of x equals 2x and g of x is equal to x over 2. In class I said 1/2 x, same thing. And my job is to prove that these two functions are identity of, are inverses of each other. Well, if they're inverses of each other, what happens is, let's go back, let's use a notation before we go ahead. F inverse of x is basically, is the inverse of f of x. Right? That's what was mentioned in class, right? So what we want to happen is if you, whichever direction you compose in, you should get back x as your output. So what's going to happen here if I take, I'm trying to make a claim that g of x is equal to the inverse of f. I'm also making a claim that f of x is the inverse of g. Again, I'm doing this for the future mathematicians here. Don't worry too much about what's in green. We're gonna get back to the blue stuff, all right? All right, so here goes. So I start out as usual. Again, we're still in 13a. I started as usual by doing f composite g. So f composite g is, again, the same thing. You're putting g of x on the inside. You're starting out with g of x. What was g of x? G of x is x over 2. Right? That's what's on the inside. And what you're doing to that now is you're operating on that with f. What does f do to its input? What does f do to its input? Well, f basically multiplies its input by 2. So 2 times, to multiply by 2 after dividing by 2, basically brings you back to where you were, where you start, what you started with. So 2 times x over 2 is just x. Similarly, if you go in the other direction, g composite f, G composite f, what you're going to have here is you're going to have f of x on the inside. F of x now becomes the input. In other words, the input now is going to be 2x. What does g do as a function? Well, g takes its input and divides it by 2. So what's 2x divided by 2? 2x divided by 2 is just x. For lack of space, this is x. Alright? So the answer is x. 2x divided by 2 is x. So in both cases, you got x for your answer. Right? That crazy looking thing is an x. So f composite g gives you x. G compose with f gives you x also. So what's your conclusion? F and g are inverses of each other because when you compose them in both directions, you got the identity function. Alright, so let's do another example. Alright, so alright, let me just write it out. Somebody's watching the video needs to see it written out. So what we're saying is that f of x equals 2x and g of x equals x over 2 are inverses. That's what we just showed a while ago. Why? Because f composite g is equal to g composite f, which is all in turn equal to x. All right, that's what we just showed. All right, so that was a proof. Welcome to proof in algebra. All right, so let's look at 13. Let's look at 13. Did I say 12a? That was 13a. All right, let's look at 13b. All right, 13b. What we want to show here is we want to show that f of x, which is equal to x plus 4 quantity cubed, and g of x, which is a cube root of x, g of x, which is a cube root of x minus 4. We want to show that these two functions are inverses. Now, let's just look at this logically for 30 seconds. What we're saying is that if you start with a number x and you add 3 to it, and you add 4 to it, start with a number x, add 4 to it, then cube that result. What we're saying is to undo that, to get back to x, the first thing you need to do is you need to take some cube root, right? And then you're going to be subtracting afterwards. So the opposite of adding then cubing is going to be taking cube root. Opposite of adding 4 then cubing is just taking the cube root and then subtracting 4. It's a reverse of the process that you had before. So quickly you start with f composite g. Basically you look at what happens when you put g of x inside as the input. Well, if you put g of x inside of f, you're going to basically now have what you have here. Need some more space. I'm going down here. What you have here, if you put g of x on the inside, what you're putting inside is going to be, you're putting inside cube root of x minus 4. That's what you're putting on the inside. So wherever you see x, you're going to replace it with the cube root of x, period, that's one thing, minus 4. So again, you put in the difference of the cube root of x and 4 wherever you see x. So this is x here, and wherever you see x, you're going to put that. But don't forget, you're also subtracting, you're also adding 4. And after all that process, now you're cubing. Well, if you're adding two things, you really don't need parentheses, right? So you can strip away the parentheses. All right, you can strip away the parentheses, and then what you have here, if you strip away the parentheses, is you're going to have cube root of x minus 4 plus 4. Well, if you're taking away something and adding it back, you're just where you started, right? So this minus 4 plus 4 cancels out, and what you have here is the cube root of x cubed. Well, cubing something and like we went over in class before, cubing something and followed by taking the cube root gets you back to what you started with, which is x. All right, and a similar process if you would reverse the order, and this time you're going to be taking G composite F, you're going to end up with x again. So let's do that quickly. So we're going to go the other direction. So this time you're starting out with, you have G composite F of x, G composite F, which is just G, and F of x is now your input. Well, if you go back to the function, what happens? What is f of x? Well, f of x is just x plus 4 cubed. And what are you doing to that? You're taking the cube root and you're subtracting 4, because that's what G does. G takes the cube root of something and then it subtracts 4. Well, you know, without going over a long process, you should see that if you take the cube root of something that is already cubed, leads you back to what you have under the radical. All right, so here we have, I'll take up this paper, the cube root and the cube undo each other. So here you have left over under the radical, and in your parentheses, just gonna have x plus 4, radical is gone, and now you're subtracting 4. So it's going to be x plus 4 minus 4, which is going to be x. So what you just showed in 13b is that you just showed that G and F were inverses of each other. So that was 13b. All right. Okay. So let's look at 13c. 13c. All right, so 13c, you are looking at the functions. F of x is equal to x squared plus 7. You're looking at the other function, g of x is equal to the square root of x minus 7. You should see a pattern here, by the way, that as far as it goes with inverses, when you're having some square and you're having some square root, then obviously you're dealing with inverses, because these are inverse operations, so to speak, or inverse processes. All right, so now I just want to show that f, I'm going to go shorthand now. So f composite G, I'm writing it as G of x inside of f. So now what's going to happen now is I'm going to put G of x on the inside. So what I'm doing now is G of x is the square root of x minus 7. All right, and that's going to be going on the inside wherever x is. But what is being done to this? What is f doing to its input? F is squaring its input and adding 7. All right. So now, if you square something that is, you're taking the square root off, all right, we say they cancel out, right? Again, we're being loose here. We're not worried about absolute values and stuff like that. All right, okay, and absolute value wouldn't come here anyway. So you're gonna have x minus 7 plus 7, which is just gonna be x. All right, so that's what you have there. Okay. So let's do one with fraction. So basically what you have now is you just showed in one direction that x minus 7 plus 7 is x. You just showed in one direction that you're halfway to showing that f and g are inverses of each other. You have to go the other direction now, which is now you want to show what happens when f becomes the input. All right, so now f is the input. So now you have g of f of x. What was f of x? F of x, if you're looking at your handout, 13c, f of x is just x squared plus 7. Right? That's what f of x is. Now, what does g do to its input? Well, g takes its input, whatever that is, and it subtracts 7 from it, and then takes the square root of it. Well, of course, here we have x squared plus 7. You don't need a set of parentheses for the first thing because you're not multiplying by the negative or anything. So this, you can just get rid of the parentheses. All right, so obviously 7 minus 7 is 0. And so now you have the square root of x squared, which is going to be x. Now, somebody might say, but the square root of x is the absolute value of x. Well, what we didn't do, because this is algebra 1, we didn't define the domain of these things. If you look at x square root of x minus 7, the domain of that has to be 7 or more. So if you're taking the square root of something squared and the original number was positive, there's no need to put an absolute value sign, because the absolute value of a positive number is the number itself. So absolute value of x would still give you x because your values are positive here. So just make a note of that. All right. Let's look at one with 2 rational functions. Example with 2 rational functions. All right. So we're going to be looking on 13D. Okay, 13D. 13D. F of x is equal to 3x plus 11 over x plus 5, and g of x is equal to 5x minus 11 over 3 minus x. All right, now this problem is going to look weird. There's another way to do this, which I wish I could do, but somebody's going to be asking questions. I learned from experience, nobody wants to have 2 processes for the same thing. So even though I have an easier process, I'm going to teach it the regular way. All right, so these are our functions, and we are going to prove that they're inverses of each other. All right, so what we're gonna do here, I'm gonna be do something a little different. I mean, give a little bit of some intermediary step. So I wanna find out what F composite G is. Well, F composite G is you basically just putting in G into F. All right, and I'm going to do that literally for this particular process here. I'm going to first shorthand it as, okay, not quite what I wanted, but I'm going to shorthand it as F. This is F right here. I literally want the blue, darker blue to be applied, dark blue to be applied to the G only. All right, so that's what I have. I have an F, and G is becoming the input. All right, I need this visual. So G is now the input. What does that mean? Wherever I see my function with F, I'm going to replace everything that I see that X does. I'm going to replace that with G. So for F, I see 3 times X, which I'm going to write as 3 times G. All right, cool. So I'm going to write that as 3 times G. Plus 11, there's no G there, so we can leave that constant. And now I have G wherever I see X. Again. Perfect. That would be good if that's all we had, but we need to go back and now just write what the G is. So what is G? G is this crazy thing here, which is going to be 5x minus 11 over 3 minus x. All right, and now I'm adding 11 to it. And under here, I have the same thing for G again. I have, what is G? The same thing, whatever that is. 5x minus 11 over 3 minus x. All right, cool. The good thing about this is that we did stuff like this before, right? So we know the least common denominator is going to be 3 minus x. So we're going to work from that frame. All right. So now I'm gonna take this. I'm gonna take this and I'm gonna just flesh it out. See what happens. I'm gonna give you an alternate way after this. This is way too long. So I have 3 5x minus 11 over 3 minus x plus 11 over 5x minus 11 over 3 minus x plus 5. All right, and so you want to multiply everything by 3 minus x. All right, and if you do that, what's going to happen, you should see, is that the 3 minus x is going to cancel this. And what you're going to have here is going to be 3 times 5x minus 11 plus, of course, this 3x is now going to multiply the 11 also. So it's going to be 11 times 3 minus x all over, again, this 3x is going to cancel this. What you're going to have is you're going to have 5x minus 11 plus 5 times 3 minus x. Of course, that's going to be in the top, 15x minus 33 plus 33 minus 11x on that. And on here, I'm going to have 5x minus 11 plus 5 3s 15 minus 5x. All right, so that's a process. Now, if you simplify this, you should see that you're gonna get 4x over 4, which is gonna be x. All right. Okay. So you're gonna have, when you simplify, again, you have 15x minus 33 plus 33 minus 11x over 5x minus 11 plus 15 minus 5x. All right, if you gather all the like terms, you should see, hopefully, that negative 33 and 33 inverses give you 0. 15x minus 11x is going to be 4x. 5x and negative 5x again, similarly opposite, so they cancel. Negative 11 plus 15 is 4. As I said before, 4x divided by 4 is just going to be x. So that's what you show. Now, I'm not going to go through the long process. This was just some mathematical meat for you to see what's going on. I'm going to show you a shorter process by which I could have verified that these two things were inverses of each other in like 25% of the time that we took. All right, so let's go back to the process. 13D. So here's an alternate method. All right, so here's an alternate method. By the way, notice that whenever you find the inverse of a function, what you're basically doing is you're basically trying to get back to the x that you started out with. You're saying, for instance, the inverse of, if you have f of x is equal to 2x, the reason why the inverse of that is half of x, because a good example is, if you think of the process, suppose x was 10. 2 times 10 is 20. The inverse is now asking you to put the 20 back into something that gives you 10. Well, you need to have a half x for that. All right, so what we're gonna do now, we're gonna look at the alternate method, 13D. All right, this whole process can be done, of finding inverses can be done by you noting, I'm gonna use color code this. You noting that f of x is basically can be written as y, right? Think of f of x as y. So f of x is equal to 3x plus 11 over x plus 5. All right? And what you're going to do basically is you're going to rewrite this as y is equal to 3x. Y is equal to 3x. I'm using the color code for a reason. 3x plus 11 over x plus 5. 3x plus 11 over x plus 5. 3x plus 11 over x plus 5. All right, so what we're going to do, the process of solving this says this, right? What we do is we replace x with y. All right, so replace x with y. All right, so what happens now is if you're replacing x with y, you're gonna have, what you're gonna have now is you're gonna have replacing x with y. Keep this in your mind. All right, change this. Replacing x with y basically means that you are going to literally put x wherever you see y, and vice versa. So now my green y now becomes that black x. So now I have x here. X is equal to 3y. X is equal to 3y, my green y now, plus 11 over, what I used to have here was x, now I have y. It's supposed to be a green y, okay. Okay, what I have now is a green y plus 5. And so we can proceed to solve by using, whatever mathematical tools we have. So now I know about cross multiplying, so I'm going to cross multiply. Right? And so what I get here is I have my x. Again, it's important for me to keep my color coding. What I have here is I have my x multiplying, x multiplies y plus 5. And that's going to be equal to my 1 multiplying 3y plus 11. Okay. And what I'm going to do now is I replace x with y, right? So now I'm just going to solve for y, okay? Because obviously that would only make sense, right? If I solve for x, then I wouldn't have to go through this process in the first. Did I solve for x? Okay, no, it wouldn't make sense because I wouldn't need what I just did a while ago. So now I have x times y is going to be x y plus 5x is equal to 3y plus 11. So if I'm going to solve for y, then obviously I need, if I'm going to solve for y, I need everything that